Okay, now we're going to try problem 10.44. This one actually is an extension of this VSEPR molecular geometry business. But it's an interesting problem and I wanted to work it. With the reason being is because we're starting to work towards describing the geometries of more complex molecules. And what I mean by that more complex is molecules with more than one central atom. In 1044, we're discussing or we're told to determine the shape around each central atom in each of the molecules and explain deviation from ideal bond angles. Okay, so we're basically given these molecules and asked to identify all the central atoms and talk about the geometry around each. And I thought it would be kind of a fun example. So A and B, two molecules, acetic acid and hydrogen peroxide. So acetic acid is one of the simplest weak organic acids that we have in the lab, we work with. It's the primary ingredient in vinegar, as it turns out. This is acetic acid. And then B, H2O2, is hydrogen peroxide. So if you are familiar kind of around your bathroom at home or wherever you keep your peroxide, in that brown bottle, the bottle that says hydrogen peroxide, this is the active ingredient in that, H2O2, okay? It degrades slowly even in that bottle over time. It's a pretty reactive molecule, as are most peroxides. So where do we go with this, okay? Well, the first step is to come up with our Lewis dot structures. And I'm going to kind of do that quickly because I want to spend most of the time on this video talking about what to do about the shapes around each central atom, because that's really kind of what this problem deals with. Now, if you were to come up with a Lewis dot structure for the acetic acid, what you would find is it's going to look like this. Okay, this is my Lewis dot structure for my acetic acid. My oxygens are over here. This arrangement of atoms is actually pretty important. Called a carboxylic acid functional group. Whenever you see that, sometimes it's abbreviated COOH. It's a carboxylic acid. It's a weak organic acid, generally speaking. So that's a common arrangement of atoms, as it turns out, in organic molecules. But nonetheless, this would be the Lewis structure of this particular substance, this active ingredient in vinegar, the acetic acid. So when we look at this, how many central atoms do we have in this molecule? Well, one is pretty easy to pick out. It's this carbon right here, right? That's central atom number 1. We'll call that number 1. This carbon also appears to me to be a central atom. Carbon's very often a central atom, almost always. Is there any other central atoms here? Well, I think there is. Looks like this oxygen. Central atom number 3. So we've actually got 3 atoms in the center, or with at least 2 bonds in this particular molecule. Okay? We want to describe the geometry around each of these. What would it actually look like, okay, if we were to see it? Well, I've drawn it kind of on the board just with these connecting lines. What might this molecule actually look like in 3-dimensional space? Well, I've taken the liberty of going ahead before I talk about this particular problem to basically build this molecule with the ball and stick model set. So you see what we have over here? This is that CH3 group, which is on the left-hand side. Okay, that's right here. Then we've got the other central carbon here. The reds are my oxygens. So notice down here I've got an oxygen bond to my hydrogen, that's my OH. And this one up here, that's my double bond, C double bond O. Okay? This is what this molecule would actually look like if I could see it in 3-dimensional space in accordance with this VSEPR theory, okay? Now, notice that looks a lot different than the way I've connected things here. So what we would like to have the ability to do as we get more and more experience with this VSEPR model is to go from a Lewis dot type structure to start thinking about what the molecule actually looks like in 3D space, okay? Because what the molecule actually looks like is going to be more important in organic chemistry, and it's also really important in biochemistry, because the shapes of molecules in biochemistry can be very, very important because given molecules will go and fit in very large molecules called proteins or enzymes and actually dock there. And their shape and the actual arrangement of atoms relative to one another becomes extremely important in terms of how that molecule functions. So we'd like to go from Lewis dot to an understanding of what the actual three-dimensional shape is. And that's what this problem is really nice at doing for us, okay? Kind of starting in that direction. So we go central atom by central atom. The neat thing about this is we can apply this VSEPR theory to each central atom kind of independently of the others to a large extent. So for instance, I look at this first carbon and I say, well, how many regions of electron density does it have around the central carbon? 1, 2, 3, 4. So there are 4 regions of electron density around that central carbon. So it must belong to the tetrahedral base family. And if I look at that carbon in my model, sure enough, I see I got one bond, one bond, one bond down here, and then this one right here, which is very visible. This carbon is what? Tetrahedral. It's got 4 bonding regions around it. The shape, the molecular geometry around it's tetrahedral. Tetrahedral carbon. In terms of hybridization, we're going to call that sp3, okay? sp3 hybridized. Now, what about the second central atom, this carbon right here? Well, look at my Lewis dot structure. Give me some guidance. How many regions of electron density? 1, 2, 3. They're all bonds. There's 0 lone pairs. 3 bonding regions, 0 lone pairs. That's also reflected in my molecular structure here. I've got my double bond up here on the top to the oxygen, single bond to this oxygen, a single bond down here to this carbon. So what shape is that? Well, 1, 2, 3 points. That kind of looks like a triangle, right? They all lie in the same plane. So can't we call the geometry here 3 bonding pairs, 3 regions of electron density? Can't we call that, or 3 bonding regions, I should say, can't we call that trigonal planar? So the shape, the molecular shape around this carbon, maybe I should stand on this side, it'll be easier, right? The molecular shape around this carbon, carbon number 1 in my structure here, is tetrahedral, but that's different than the arrangement of atoms around this carbon. This carbon is trigonal planar. You see the shape around the carbon, the arrangement of the other atoms is different. Here, it's a triangle in a plane. But the carbon over here, it's got that tetrahedral arrangement. It's different shape around that carbon. So each central atom can have its own shape. Okay, that's kind of the idea here. Now we have one more central atom to consider, and that's this oxygen over here, number 3 in our structure. Okay, but we go about answering what the geometry is in largely the same way each time. We look at our Lewis structure, we figure out how many regions of electron density there are. There are 2 bonds and 2 lone pairs. That makes 4 regions of electron density around that central atom. There are indeed 4 regions of electron density around that central atom, but the thing is that 2 of those regions are going to be what? 2 of these regions are lone pairs. Now where would those lone pairs reside? Well, if I kind of turn this in this way, and here's that end-on view of that oxygen, one lone pair would kind of be up here, and the other lone pair would kind of be up here. They're just not shown because I don't have a way to show these lone pairs here, okay? But one will be like here, the other one will be in here. In space, they still take up space and they affect the shape of the molecule because it's a region of electron density, but they don't necessarily describe the molecular geometry around this atom. So while the base geometry is tetrahedral, 2 of those lobes have been replaced. Okay, the base shape is the same as this carbon, I guess you can say, right? Because it's a tetrahedron shape, but it's 2 of those are gone now, right? And all we're left with is this bond and this bond, okay? You can see that reflected over here. So that's reminiscent of then this bit geometry. Let's It's the same geometry reflected in water. It's called bent. Okay? So, we have these different central atoms, and each of them take on their own shape. We apply the Vesper theory to each individually, and the net result of this is that we can build relatively complicated, complex three-dimensional molecules or structures by considering each central atom individually. Okay? That's kind of the beauty of what we're doing with this. Now, second molecule is hydrogen peroxide H2O2. In this particular molecule, we would have 14 valence electrons to play with. I'm drawing my Lewis dot. I believe I come up with something that looks like this for a viable solution. Remember, hydrogens only need a duet or 2 electrons, and they form one bond. The oxygens like to have 8 or an octet, so this one's got 4 plus 4 is 8. 4 plus 4 is 8. We've got 2, 4, 6, 8, 10, 12, 14 electrons used. It's consistent with how many we had. And I also knew that this word peroxide is reminiscent of the case where we have oxygens bonded together in the structure. Okay? So this is the arrangement of atoms in the Lewis dot structure for hydrogen peroxide. But we don't necessarily want to know about the arrangement of atoms here. We want to know about what is the geometry around the central atoms. So again, how many central atoms do I have? Well, hydrogen is never a central atom. But in this particular case, I've got these 2 oxygens, both of which have 2 bonds. So each oxygen is itself a central atom. So I'll number them oxygen 1 and oxygen 2, just for reference here in this discussion. What do we think about this? Are these 2 oxygens essentially the same in terms of their structure around the central atom? I think that maybe they are. Don't they both have 2 bonds to the oxygens and also 2 lone pairs? So 2 bonding pairs, 2 lone pairs. They're essentially identical in terms of shape. Now, they're different oxygens, right? They're different central atoms, but they have the same shape. So what would be that shape then? Well, they have 4 regions of electron density. So as a consequence of having 4 regions, we're in that tetrahedral base family. But 2 of them are lone pairs, okay? So as a result, we have what's referred to as the bent structure, okay? If we start with, let me see if I can find my base tetrahedral. Here's one I can put together real fast. We start with my base tetrahedral shape, which is this, right? 4 bonds here to different atoms, right? And I'm going to replace any 2 of them with a lone pair, so I'm going to remove the atoms that are bonded. What I'm left with is this nice little bent shape, right? See that? So each central atom in hydrogen peroxide takes on that bent geometry, and as a result, the final molecule would look something like this, right? We have O2, hydrogen, hydrogen, H2O2, peroxide. Both central atoms have this bent geometry. You can see that reflected in my model, and that would be the geometry around both central atoms here, okay? So hopefully in this example problem, you can see how we extended the Vesper theory considering one central atom to having multiple central atoms in the same molecule. And it's really useful because, again, it allows us to predict the shapes of much more complex molecules than just the simple ones we originally started thinking about, okay? And that can be really important for the molecule's function, as it turns out. It's also super important for what's known as molecular polarity, which is going to be a topic that we're going to consider next here, I believe, in this chapter. Molecular polarity is a very important concept for describing how collections of molecules behave. It affects the physical properties of materials very, very dramatically. And this Vesper business directly is applied to predicting molecular polarity. You have to know Vesper to polarity. So if this is all sequential. You need to know Lewis dot to do Vesper and predict the shapes of molecules. Once you can predict the shapes of molecules, you can predict if they're polar or not. If you can predict if they're polar or not, you can start to make some predictions or understanding about the molecule's physical properties, its boiling point, how viscous it is, things like that, okay? So that's again why this is really important to not fall behind in this chapter. You really got to keep up on top of things on these concepts if you're going to kind of link one thing to another, and that's sort of a requirement for where we're headed. Okay, so keep that in mind.